Hi there, thank you for checking out my poster. I'll walk you through my functional imaging study where we used multivoxel pattern analysis to investigate how perceived similarity is represented in our brains. Specifically, we were interested in the medial temporal lobe region perirhinal cortex and downstream region anterolateral entorhinal cortex. It's been suggested that these regions form an extension of the ventral visual stream for object processing, but we don't know whether they represent perceived visual similarities, and if so, at what level. To investigate if these regions reflect the perceived similarity of highly similar objects, we needed to have many objects with varying degrees of visual similarity. This study included 4 exemplars from 10 object categories from the MIGO database. Importantly, all participants rated these objects based on how visually similar they perceived the objects in each category to be. This was done offline using the inverse multidimensional scaling task adapted from Kriegeskorte and Murr 2012. These distances in the IMDS task were converted to dissimilarity percentile to create the behavior-based perceived similarity representational dissimilarity matrix, which we will use in behavioral and fMRI analyses. The main experiment was completed in a 3T scanner. The task was a variation of a one-back task that we call Category Exemplar One-Back Task. Like in a classic one-back task, participants are shown a stream of object images one at a time and indicate with a button press when the object is exactly the same as the one previous, or what we call the same exemplar. Our novel twist is the addition of a second button press to indicate when the object is the same category as the one previous. When the object is a different category, no button press is required. These are the majority of trials and are used to probe fMRI pattern similarities. The catch trials, however, are there to make sure participants are paying close attention, as this task relies on processing the object as a whole rather than using low-level features. We analyzed the catch trials and found that participants' behavior on this task is sensitive to perceived similarity. The proportion of errors increased as the level of perceived similarity increased, and this positive linear trend is larger when using participants' own similarity ratings. To analyze the functional data, from each ROI we extracted the mean activation pattern from the 24 no-response presentations of each exemplar. The 6 pairwise pattern dissimilarities between the 4 objects in a category were used to compute the brain-based representational dissimilarity matrix. The metric that we present here is the Brain Behavior I-Index, which is calculated by subtracting the between-subject brain behavior correlation from the within-subject. Using bootstrapping, we can conclude that if the I-Index is significantly greater than the null distribution, then the patterns in that region reflect participants' own similarity ratings more so than other participants' ratings. Plotting the I-index from 8 ROIs from early visual cortex to temporal pole, we see that only activation patterns in perirhinal cortex and anterolateral entorhinal cortex correlate more with participants' own ratings compared with correlations with other participants' ratings. And this is greater than any other region, including earlier ventral visual stream regions. Additionally, we can see a nice divide between anterolateral and posterior medial subregions of the entorhinal cortex. The posterior region has been linked more so to perihippocampal cortex and scene processing. Now, we wanted to see if there is any difference in I-index for the different levels of perceived similarity. We see that only patterns in perirhinal cortex and anterolateral entorhinal cortex reflect the highest levels of perceived similarity, again in this individually unique manner. And we see our searchlight analyses confirm our ROI findings, where only perirhinal cortex and anterolateral entorhinal cortex patterns reflect the highest perceived similarity representational dissimilarity matrix. To summarize, we see that fMRI activation patterns in perirhinal cortex and anterolateral entorhinal cortex but not posterior medial entorhinal cortex and perihippocampal cortex, reflect the perceived similarity of objects unique to the individual, and their patterns relate to the highest levels of perceived similarity that earlier ventral visual stream regions do not. Our findings suggest that perirhinal cortex and downstream anterolateral entorhinal cortex may not just be part, but the pinnacle of the ventral visual stream for object processing. Thanks for checking out my poster.